Hello, everyone. So today, your midterms are coming right up. And so I'm recording basically me solving one of the review worksheets. And I'll be doing the HMMs worksheet because that's the content that you've had the least experience with. So as you see, this first page is kind of just a summary of what's up with HMMs. So you have these state variables and these evidence variables. And you just see two of them here, but really it goes on to W3 and O3, which is shaded, and W4 and O4, and so on. And you get these get transition models. So you have the probabilities for these areas here in purple that we assume are all the same. That's probably probability of WT plus 1 given WT. And you also have these sensor models. So for these downwards arrows, we assume that it's always the same probability distribution. It's probability observation T given world T, I guess. So I guess that's what I would call W. And there's this joint distribution of the hidden Markov model that you can factorize nicely. That's just probability of all the worlds and all the observations is the initial world. And then, okay, next world given the previous world and given observation given that world. And those are all things that we are given. So we're interested in this problem of state estimation. Like, given that we can see the O's, what are the W's? And we kind of have this nice algorithm to do that, right? Your B and your B prime, you can use them to update each other. So B is just what you know about state T given up to and including T. B prime is what you know about state T given up to, but not including state T, time step T, all those observations. So basically what you can do is you can say, okay, well, given that you get what's your probability of the next world given all the observations that you have? That's B prime, WT plus 1. That's just sum over, possible worlds that you could have been in at time T, how likely you were in those worlds, and what's the probability of the next world given that world. And then the observation update is a time T plus 1. Given that you see what the actual observation is at T plus 1, well, it's just proportional to observation at time T plus 1, the world at time T plus 1, times your prior over what world you might have been time T plus 1. So this let me square it in green. This equation right here, this is basically just Bayes' theorem. And the one difference to Bayes' theorem is that it's proportional. So we're not actually writing out the full normalization step. We're just saying it's proportional to this thing. But yeah, it's sort of Bayes' rule of like probability of the world given your new observation, essentially. So that's the forward algorithm, just for each state, all the probability of all the ways you could have gotten to that state. Then there's the Viterbi algorithm. So that's basically for each state, what's the maximum probability way that you could get to that state? So that's kind of like saying, okay, I want like just a single story of what happened in all the hidden states. And so what that is solving for the argmax of probability of your sequence of worlds given your sequence of observations that has a forward pass and a backward pass that that's described in lectures. So let's look at these problems. So the first one is we've got this hidden Markov model, and it's very we're kind of only looking at 2 time steps here. It's quite a simple one. So W1, W2, and we have this initial conditional probability table, initial CPT, which is just it's just really a vector. This CPT for the worlds given the worlds. So this is I guess the state dynamics. And the third one is observations given worlds. So that's like a sensor model. You can kind of think of it. All right, so we're observing O1 is A and O2 is B. So now our job is to use the forward algorithm. So we want to get a probability distribution of W2, given that O1 is A and O2 is B. And we're going to do that one step at a time. So first, what's the probability of world 1 and O1 is A? So it's just joint probability. Well, probability of W1 no 1 equals A. We can just expand that using basically the definition of conditional probability. That's probability W1 times probability that O1 equals A given W1. And the reason we do this is that now these are just the tables we have, right? So we can sub in different values of W1. So probability that W1 equals 0 and observation 1 equals A. Well, probability W1 is 0. That's 0.3. We can see in this table. So 0.3 times probability O1 is A given W1 is 0. So O1 is A given W1 is 0. That's probability of 0.9. So 0.3 times 0.9. That's equal to 0.27. Now, what's the probability that W1 equals 1 and O1 equals A? Well, that's just the other entries, right? So W1 equals 1, that's got a probability of 0.7. And O1 is A given W1 is 1. That's 0.5. So 0.7 times 0.5 is equal to 0.35. Now we've got to calculate probability of W2 and O1 equals A. So probability of W2 and O1 equals A. Well, we can kind of expand that out, right? That's sum over values of W1, probability of little W1 and O1 equals A times probability of big W2 given W1. And we can do this because this is like the Bayes rule expansion, except we're using the fact that W2 is independent of O1 given W1. So we're sort of looking, okay, you know, what are all the W1s that can make this whole story work? So what's this? How do we cash this out? So what's probability that W2 is 0 and O1 equals A? Well, that's probability W1 equals 0, O1 equals A, times probability W2 equals 0, given W1 equals 0 plus probability of W1 equals 1 and O1 equals A times probability that W2 is 0 given that W1 equals 1. All right, and now we can read these off the conditional probability tables and off of this stuff that we were lucky enough to have just calculated. So W1 is 0, O1 is A, that's 0.27 times W2 is 0 given W1 is 0. Pardon me. W2 is 0 given W1 is 0. That is 0.4 plus, okay, W1 is 1, O1 is A. We calculated that, that's 0.35. And W2 is 0 given W1 is 1. That is 0.8. And if you calculate that out, that's equal to 0.388. I'm lucky to have the answer in front of me. I can't just do that in my head. All right, and to make some room, I'll just get rid of, here's what I'll do. I'll just move it over. I'll put this, okay, I'll delete it, sorry. But you can just pause the video and look back at this expression if you want to. All right, 0.388. And of course, we're going to use this later, just like we used the previous step. So next, probability W2 is 1 and O1 equals A. Well, that's probability W1 is 0, O1 is A, times probability W2 is 1, given that W1 is 0, plus probability that W1 is 1 and O1 equals A, times probability that W2 equals 1, given that W1 equals 1. Now, this first term, we can look it up just, from the green stuff, that's 0.27. Second term, W2 is 1, given W1 is 0. That's this the second conditional probability table. This one right here, that's 0.6. Plus W1 is 1 and O1 is A. We can look it up in the green highlighted stuff. That's 0.35. And W2 is 1 given W1 is 1. Again, the conditional probability table, that's 0.2. And that ends up being equal to 0.232. And again, I'll raise all of this working out just so that it fits on the page. But don't be fooled. I really did have to work it out. All right, let's highlight this in another nice, let's highlight it in blue. All right, now we're going to also compute the joint where of W2 and O1 is A and O2 is B. So how do we do this? Well, probability of W2 and O1 is A and O2 is B. That's equal to probability of W2 and O1 equals A times probability that O2 equals B given W2 and O1 equals A. So this is just true by the, just by the definition of conditional probability, where we're conditioning on W2 and O1 is A. But we can simplify this a bit because like O2 is independent of O1, conditioned on W2 in the base net that we've circled in red at the top. So actually, we can just kind of erase this. And now we see that this is exactly one of the terms in our probability table. So we can just calculate it out. Okay. So probability that W2 equals 0, O1 equals A, O2 equals B. Well, looking at the blue, so W2 is 0, O1 is A, that's 0.388 times O2 is B given W2. Well, we can look at the third conditional probability table. O2 is B given W2 is 0. That's probability of 0.1. And, well, that's 0.0388. Next, probability that W2 equals 1, O1 equals A, O2 equals B. Again, we can just substitute it in. Now we use 0.232 from the blue. And from the third conditional probability table, probability like OT is B, given that WT is 1, that's 0.5. And that is equal to 0.116. All right, so let's highlight this. We're nearly running out of colors, but let's highlight it in a lovely purple. So finally, we've got to compute probability of W2 given O1 is A and O2 is B. So, well, we have the joint, right? So we just have to renormalize the distribution. So probability that W2 equals 0, given that O1 is A and O2 is B, well, that's equal to probability of W2 equals 0, O1 equals A, O2 equals B, divided by probability W2 is 0, O1 is A, O2 is B, plus probability W2 equals 1, O1 equals A, O2 equals B. And just looking that up from the purple, so the top is 0.0388, rather, sorry. So 0.0388. The first term at the bottom is also 0.0388. And the second term is 0.116. And that's equal to around a quarter. And what's probability W2 is 1, given O1 is A and O2 is B? Well, it's sort of the same thing, but we swap the role of the two numbers. So 0.116 over 0.0388 plus 0.116. And that's around equal to 0.75. And we could also have just subtracted 1 from 0.25 because, probabilities add to 1. So that's that problem. And how is that related to the forward algorithm? Well, remember the forward algorithm had like the B primes and the Bs. So the B primes was our credence in the was our belief about the state WT. B prime was belief about WT given all the observations up to time step T. And so up to but not including time step T. So you can see in this step, we're basically doing that, but instead of conditioning on O1 is A, we're doing the joint. But that's not really important because we could have just renormalized. So the thing we're doing is it's slightly different to a probability. And that's because really the B's, where you're getting the current state given all the observations up to now, is in this step and in this step. Except, in these places where I've drawn the green arrows, it's like the joints of like whatever this current state is and the current observation rather than conditioned on the current observation. And so you need to renormalize at the end here. But, you could have been renormalizing like all the way along. And I guess like it's sort of useful to know that you can choose to wait until the end to renormalize. But the problem is, then your numbers are going to be like very, very small. And, if you only have so many digits in your computers, maybe you want to, maybe that's not a thing you want to do. Well, all right. So that was question 1. I hope that wasn't too crazy for you. Next is question 2. And I guess this is kind of harder because, that's not quite a HMM. It's a little bit different. So in the near future, autonomous robots would live among us. Therefore, it's important for the robots to know how to properly act in the presence of humans. Darn right. In this question, we're exploring a simplified model of this interaction. So we observe the robot's actions at time t, which is big RT. So that's these variables. And we also have an evidence observation. So we're kind of thinking from the robot's perspective. So the robot chooses actions R, given evidence. So what the robot can see of the human action, which is here at the top. So the human action is unobserved to the robot. And what happens is like, given what the human used to do, given what the human did previously, and the robot's previous action, both of those inform what the human does next. So we have, let's draw it in yellow. We have like this arrow here, and that looks terrible. We have, do it in green, this arrow here, and this arrow going up here. So a human at time t depends on what the human did, t-1, and what the robot did, t-1. All right. So we have the kind of the standard probability tables. And we're going to derive the forward algorithm for this model. And hopefully this gives you a sense of like how people end up deriving algorithms like this. So we're going to do it in kind of two ways, right? We have the time elapse expression and the observe update expression, and they're going to kind of depend on each other recursively. So we're going to assume that we have access to this time elapse equation. So time, big T of HT is probability of HT given all the evidence, all the observations of the human's action up to t-1, and the robot actions up to t-1. So now we want to compute. What do we want to compute? What we want to compute is probability of big H time t given evidence of 0 up to time t and the robot actions from 0 to time t. What's that equal to? Well, that's equal to, actually, I'll just add a page so that I can have space to work. So we can kind of use the definition of conditional probability, right? So that's probability of big HT and evidence 0 up to t and robot actions 0 up to t divided by sum. That's not a good sum. Divided by sum over all the possible ways it could be of probability of little h t, evidence 0 up to t, robot action 0 up to t. Right. Now, how can we write this out? Well, that is, and we'd like to use like capital T. We'd like to use this probability of HT up to E0 to t-1, R0 to t-1. So up the top, that's big T of HT times probability of E0 up to t and R0 up to t, right? Oh, no, sorry. So what I'm going to do, actually, I'll just explain what I'm going to do. I'm going to decompose the top into probability of HT E0 to t-1, R0 to t-1 times probability of ET and RT given HT E0 to t-1, R0 to t-1, right? And the reason that I'm doing that is because I want to use this capital T of HT, and that has, HT, E up to t-1 and R up to t-1. So this first term is kind of going to be that. So moving it to the left a bit to give us some space. So we have that in the numerator, and in the denominator, we have sum over little h of t of essentially the same thing. So I'm going to copy it down, and I'm going to replace uppercase h with lowercase h. So this uppercase h is now lowercase, and this uppercase h is also now lowercase. All right, so now how do we break apart these two terms? Well, what's the probability of big H t E0 to t-1, R0 to t-1? Well, it's the probability of E0 to t-1 and R0 to t-1 times probability of big H time t, given e 0 to t minus 1 and r 0 to t minus 1. So this term right here is our capital T, right? So it's good. We somehow worked that in. And now what's the probability of e time t and r time t given big HT, e 0 to t minus 1, r 0 to t minus 1? Well, we can kind of look at if we look at the diagram, right? Just erasing all of this. Well, ET, the way ET is like just dependent on HT. And RT is just dependent on ET. Right? That's this conditional probability relation that we have. So what this is equal to is just probability of ET given capital HT times probability of little RT given ET. And this is good because probability of RT given ET, that's something that we have. And probability of ET given HT, it's also something we have. Right? So now we've only got this one factor that we don't understand, but if we're lucky, it will just vanish. So I didn't draw that circle well. Oh, that's terrible. Right, this factor we don't have a good term for, but we're gonna see it's gonna cancel out, and so everything's gonna be fine. Don't worry. So let's sub that into the fraction up above. So this thing is equal to probability of e 0 to t minus 1, r 0 to t minus 1 times, well, I'll just call it, big T of HT, just for space, times probability of ET given big HT times probability of RT given ET. And now on the bottom, I've got sum over little ht, and the bottom was just the top with big HT replaced by little ht, and you're summing over it. So again, I'll copy it over, copy, paste. And this occurrence of big H are replaced by little h, and this occurrence of big H are replaced by little h. All right. So now we see that the top and the bottom both have this red term, and this red term doesn't depend on little ht, so we can move it outside the sum. So I'll move the sum around there. Oh, I can't do that. All right. So the sum is here where it should be, and this term on the outside is out here, and so we can cancel it out like it doesn't exist. All right, so now we have this expression, right? And we'll go back up and see what's equal to that expression. So the first one, probability HT given E0 to T minus 1, R0 to T minus 1. So that's just really big T of HT. PET given HT, PRT given ET. Well, that's exactly what we had in the numerator. And the denominator is also exactly what we had in the numerator. So this is makes a valid independence assumptions and evaluates to the next observation update expression. Because yeah, all we were doing here was this thing we were finding is exactly equal to big O of HT. All right, so the next one, probability HT given E0 to T minus 1. So it's the same thing, but we got rid of this factor probability RT given ET. We can kind of see that it doesn't depend on H, so we can also move it outside the sum on the bottom, right? So I'll just do that. We'll get rid of this floating times, and it's the same on the top of the bottom, and so we can also cancel it out. And that's exactly this expression right here. So next one is probability ht given 0 t minus 1, r0 t minus 1, et given ht. So the numerator is right, but the denominator has this et given rt minus 1 and ht minus 1. So in order for that to be correct, that would have to be equal to probability et given ht. But just because you know rt minus 1 and ht minus 1, that doesn't totally determine ht, right? Like ht is influenced by both of those things, but it's still kind of probabilistic. Like if you actually know ht, you know more than just if you knew rt minus 1 and ht minus 1. So this is not it. Next one, you're summing over rt minus 1 ht given e0 to t minus 1, r0 to t minus 1, probably rt minus 1, et minus 1. Yeah, this is not, why isn't this it? So basically we're saying we're getting like what we know about ht here, and we're factoring in like given like these things. Sorry, we're saying, okay, take what we know about ht given like all of this evidence, and then take into account like these two things. So you're not even taking into account the new evidence that you got at time t, which is like we're supposed to find this, right? So this can't possibly be right. Here we're taking into account et, which is good, in this one. So, but the problem is we're just we're conditioning RT on ET, but we're not saying how likely the new evidence was given HT, right? So in this expression, it's like we're saying, oh yeah, I can tell you how likely the state of the world is given this observation that I've just made, but you're not using how likely the observation that you just made is given that state of the world. And that's not how Bayesian inference works, or just inference in general. So this can't possibly be right, and in fact it's not right. So big X next to that. Now you're summing over the possible next hypotheses, probability next hypothesis given RT. So this again doesn't use ET, right? Like you're observing ET, your expression should like involve what ET is, but it doesn't. So this is also wrong. All right, so I don't know, hopefully that made sense. Next, we're doing the time-lapse update expression, right? So you want to use the probability tables provided in the question. And what were those probability tables? We had probability of RT given ET, probability of HT given HT minus 1, RT minus 1. I'll move this up here. We also had probability of H0, and we had probability of ET given HT. All right. So now we want to find the time-lapse update above. So HT given E0 to T minus 1, R0 to T minus 1. What's that equal to? Well, we can kind of just, so how are we going to do this? So we need to use the observe update equation. So this OHT minus 1, right? So let's try and write it in terms of that. So probably HT given E0 to T minus 1, R0 to T minus 1. I'll just write it out here so that I'm not slowing up that space. HT E0 to T minus 1, R0 to T minus 1. Well, that's we can just sum over all the possible values of little h t minus 1, right? So it's probability big H t, little h t minus 1. So this is just marginalization given e 0 to t minus 1, r 0 to t minus 1. So you know, we sort of snuck in ht minus 1 into the probability. So that's good. So now we kind of need to get like just this part on its own, right? And that's going to be O of ht minus 1. But we can do that. We can say, okay, well, this is equal to sum over ht minus 1. So that's probability of ht minus 1 given e 0 to t minus 1 r 0 to t minus 1. Oh, there we go. Times probability of big ht given little ht e 0 to t minus 1 and r 0 to t minus 1. Right? So because that's just how it works. This is how probability theory works. But we have conditional independence relations, right? So ht, once you know big ht minus 1, once you know rt minus 1, like I forgot to write this ht minus 1 here. So once you know little ht minus 1 and rt minus 1, none of these you know, this variable here, none of these variables matter at all. This ht minus 1, this rt minus 1, screen them off. So this first conditional probability expression here, we can just rewrite it as sum over little h t minus 1. So this first term is just O of h t minus 1. And then the second term, that's just probability big H t given little h t minus 1, little r t minus 1. That's the only thing that mattered. And that's it. So like, if you look at that, O of ht minus 1, that's something we have. And then probability of ht given ht minus 1, rt minus 1. Well, that's, oh, I shouldn't have used red. If I highlight that in blue, that's this conditional probability term here that we have. So we can just write that out. Sum over little h t minus 1, O h t minus 1 times probability big H t conditioned on h t minus 1, r t minus 1. All right, so that's the worksheet. I hope that gave you a sense of like how we derive these algorithms and how we kind of think about what we're doing when we write these algorithms. Because like really, this forward algorithm, all you're doing is you're just using the rules of probability theory and facts you know about conditional independences. And you're just like using those and trying to finagle the thing you want into a sequence of things that you already have. And I guess the only like special thing is you have this like mutual recursion thing, right? Like O depends on T, which depends on O, and eventually like you know, you can think about what O of H0 or you can think about what T of H0 is to figure out where that recursion ends. But yeah, this really is the kind of thing that, you know, you could basically just invent yourself. So I hope that made it make sense, and I wish you the best of luck on your midterms. Well, I'll talk to you next week. Goodbye.